introduction to control, let's say, because you will need to know Laplace transform. You might have forgotten.
Sir, too much lag, sir.
Lag in video or audio. So the kind of systems that you are going to handle in control systems in your control system course are very, very simple. They are called linear time invariant systems. Linear time invariant. In short, LTI system. That means in your model equation, so far whatever I have taught you, they are all linear time invariant systems. You don't have time bearing mass, you don't have a stiffness which is time bearing, you don't have a fulcrum which is moving horizontally. Those things become time bearing systems. So now you have everything is taught is time invariant system. All parameters are constant, they don't change with time. And the system is linear when you do not have parameters which are also functions of states. Okay? For example, a spring whose force is square spring, let's say force is K mod X X. That is a nonlinear system. We will do some simulations of nonlinear systems, but in control systems, we will only deal with linear systems. So there will be linear and time invariant or LTI systems. So usual Laplace transform definition, you know, Laplace transform of Ft minus St S dt. So we write it as F S. So some basic things, what you know is Laplace transform of integration of Ft dt is Fs into 1 by S, Fs by S. Laplace transform of dft by dt is opposite, S times Fs minus F0. Okay? So this is one condition. If you have square thing, square of Laplace transform of d square ft by dt, what do? Again, we multiply like this, S into Laplace transform of SFS minus F0 minus F gas.
So the input and output Fs are different, right?
F, this is F of S. F of S.
No, sir,
Function
I
defined
mean,
in S domain. Okay.
so,
That is function in time domain, that is function in S domain. Okay. For example, let's say your Ft is equal to constant, let's say C. Then what is Fs? Fs is C by S. Okay, constant Laplace transform is 1 by S. Alright? Okay. Let's say Ft is sin omega t. Then you will have omega square by S square plus omega square. Right. So it is F of S means Laplace transform of Ft. F of S means Laplace transform of Ft. Right. Okay. Right. So it's a function of S, but it's Laplace transform of Ft. Right. It means you don't write that Ft is equal to sin omega t. Sin omega t and Fs is equal to sin omega S. No, not that. Okay. Fs is this is omega. Sine is S omega square. Omega square by S square plus omega square. Okay. So whatever real Laplace transform comes. All right. So it's not same function. So as you go on like that, so our derivatives and other things you will get f0, f dash 0, and so on. Then Laplace transform of constant, Laplace transform of constant. I am writing it UST is equal to 1 by S. UST is unit step function. This time, this is ft, unit step at t. The function is simply, before that it was 0, oh, this is 1. Okay? Right. After 0, t is equal to 0, it is 1. That is unit step function. So these are basic definitions. Laplace transform of delta t is 1. That is, delta t is unit impulse. Obviously, when you put there, okay, e to the power minus st dt. If you put first one UST, it will be e to the power minus st dt, and when you put 0 to infinity integration, you will get 1 by s. Right. Similarly, what is unit impulse? Right. Unit impulse is t some height, let's say h, let's say epsilon. Right. This h is equal to 1 by epsilon. H is equal to 1 by epsilon. Okay. So limit of this function, right, epsilon tending to 0. Right. That is delta. So what does it exist? Right. So this is existing only at t is equal to 0, where integration of this function, integration of delta t dt, right, from 0 minus to infinity is 1. So its unit impulse means, okay, it's a large value that exists only at t is equal to 0. After that, it is 0. And its integration, total integration is 1. That is unit step function. So obviously, right, UST is integral of delta t dt. So US S is 1 by S times delta of S. It is 1 by S. Delta of S is 1. Alright? Likewise, there is a ramp. T, this is whatever function ramp, you write UI. Ramp is just straight line, a linear line. So URT equal to basically T. And this is again what? URT is integration of unit step dt. So URT's Laplace transform is S times Laplace transform of US unit step S. That is, sorry, integration 1 by s. 1 by s times unit step s, that is 1 by s square. So basic functions are, you have unit impulse whose Laplace transform is 1, you have unit step whose Laplace transform is 1 by s, you have also ramp whose Laplace transform is 1 by s square. Some constant might be multiplied. You may not have unit step, you may have, let's say, 10. So the data is giving 10, it's constant 10. Then Laplace transform is 10 by s. Likewise, you have sine and cos. So those will come later. So this is basic Laplace transform. Then we have two theorems, final value theorem and initial value theorem. Remember your transform calculus course? Okay. We are not worried about initial value theorem, we will write final value theorem. It says, limit t tending to infinity of ft equal to limit s tending to 0 s times f s, where ft is a convergent function. So if you are a function, any function, its final value will be limit of s tending to 0 fs. That is it. For example, if you take that unit step, say ft is equal to constant 10, for example. Then s is equal to 10 by s. So limit t tending to infinity ft is basically 10, and limit s tending to 0 s times fs, that is also 10. So both are same. So this is a very simple example. You can have many other complex examples. We will come to it. Okay. So this is very important final value theorem. That limit t tending to 0, this is this. Obviously, Laplace transform exists for analytic functions. Okay. So there are many things for which Laplace transform do not exist. We are not going to deal with those kind of systems.
Sir,
Yes.
sir, a little bit above you discussed the Laplace transform of a delta function.
Yes. Dirac
Sir,
delta.
shouldn't it be 1, sir?
It is 1.
Sir, you wrote 1 by s.
That is for step function. UST. Dirac delta is delta.
Oh, got it, sir.
Okay. Dirac delta's integration is unit step, which is 1 by s. Unit step integration is ramp, which is 1 by s square, and so on.
Yes, sir. My mistake.
No, it's okay. Okay. So with this, I am going to introduce a very important concept called definition of transfer function. Many people abbreviate this as TF, means all students abbreviate it as TF. It's not written as TF. Never. Okay. TF is transformer of one graph. It's not TF. I will not abbreviate it as TF. I would rather write it as this can be written as TS S dot dot dot. Okay, normal control theory, we use these kind of symbols. Okay, we don't write here. So what is this transfer function? Transfer function is, it is the ratio of Laplace transform of output to the Laplace transform of input Laplace transform of output to the Laplace transform of input for LTI systems, linear time invariant system, with a very important condition: all initial conditions set 0. All initial conditions set to 0. This is very important. So what it is? It is ratio of Laplace transform of output to the Laplace transform of input for linear time invariant system with all initial conditions set to 0. Why that? I will show you. Why that all initial conditions set to 0? That I will show. So what we have? We have a system. Whole system I am writing as a block. Input to it is ut. Output is yt. We have written our state space equation. Okay? Yt is, you know, okay, what it is. This is dx plus du. dxt plus du. That we know. This is the output. So this is input, this is output. Now we define GS, transfer function GS, of S equal to Laplace transform of yt divided by Laplace transform of t, that is y of S by u of S, with all x naught is equal to 0. All initial conditions are 0. Okay? The displacement, deformation, the momentum, whatever they are, in whichever domain, all initial conditions are 0. Then only it is a transfer function. Otherwise, it's not a transfer function. So is this definition clear? It is Laplace transform of output divided by Laplace transform of input. Some people say, hey, by mistake, they say, hey, GS is equal to Laplace transform of output by input. It's wrong. Okay? This is the correct one. Laplace transform of output divided by Laplace transform of input. Not output by input and then Laplace transform. There are two Laplace transforms involved. Laplace transform of output divided by Laplace transform of input. So this must be very clear that all initial conditions have to be 0. Laplace transform of output and Laplace transform of input should be calculated. Their ratio, that is ds obviously it's in S domain. So in S domain, we write Laplace domain, Laplace, or it's also called frequency domain. Frequency domain, S is equal to J omega. Okay, that's the usual Laplacian definition. So you have US, system is GS, output is YS. This GS is system. So this is what is a transfer function. Yes, any question? So there is another definition. Transfer function is Laplace transform of output when the input is unit impulse and all initial conditions are zero. So this is basically a corollary of the first one. We have PS is equal to YS by US. So if US UT equal to delta T, US is equal to 1, then GS is equal to YS. That is Laplace transform of YT. Alright? So if you have unit impulse as input, the output is Laplace transform of output is the transfer function. And this is usually used in experiments to find frequency response function. So those who do some kind of experiments on bearings or some other structural things, they just give a hit, one hit with something called an impulse hammer. So they give an impulse hammer one hit, they measure something from some sensor, they take a Fourier transform of that, which is equivalent to Laplace transform, and then from that they find out what is the transfer function of the system. So you give unit impulse input, measure the output, take it Laplace transform, you get transfer function. So that is the definition that is derived from the main definition. Alright, so you can have this. So let's see our first transfer function. Let's see. We have to define an output. So without output, Laplace transform function is not defined. What do you want to measure? Let's say velocity sensor. we also have, let's say, displacement sensor. This displacement sensor doesn't exist. It's integration of from velocity sensor. So what we have? We have our equation mx double dot time t plus r x dot t plus k x t equal to f t. That is our starting equation. Take Laplace transform of both sides. Okay, we are taking Laplace transform of both sides. Let Laplace transform of xt equal to x s. Then Laplace transform of x dot t, how much? S times xs minus x0. This x0 is 0. Initial condition is 0. All initial 0. So x at t is equal to 0 will be 0. Likewise, when we take Laplace transform of x double dot t, we will have s times this ssx minus x0, that is already gone, minus x dot 0, this also will be gone. So this is important. Okay. Unless you have this, you cannot define a transfer function. So what do we have after taking this Laplace transform? So this will be basically a square x s, and this will be s x s. So I have a x square xs plus rs xs plus k xs equal to whatever our applied forcing, its Laplace transform. So what is our US? This is our input. Our US. What is YS? It. YS is equal to XS. That is displacement sensor. Or output. If suppose output is XS, then we have then YS by S, that is XS by FS. That gives us 1 by ms square plus rs plus k. This is what is we get our transfer function. Or ds equal to 1 by s square plus rs plus k. This is transfer function. You know this from your dynamics course. Right. You know it very well. If you put S is equal to j omega in this one, you will get frequency response function. And if y s is equal or yt is equal to h dot t or velocity sensor, then ys is equal to s x s. Of course, initial conditions are taken 0. So then, what we have, ys by s will turn out to be s times this dx. So we have already found out, okay, sxs by ds, I will write it. S times x by s, s times x. So this then this g, so g bar, let's say s equal to s by ms square plus rs plus k. This is again transfer function or velocity sensor or displacement sensor. So the numerator of transfer function will change. So this is important to note here that numerator of transfer function changes with sensors. Number 1. Number 2, denominator does not depend on type of sensor and the input. It doesn't depend. Whatever input happens, whatever outputs are there, denominator does not change. Numerator changes with sensors. We will also show that numerator will change with the sources. So numerator of transfer function changes with sensors and sources. Sources, but denominator does not change with the input. The denominator decides the stability of the system. How it decides, I will tell you afterwards. So I will formally write the transfer function in another form. ds equal to ns by ds. Ns is numerator polynomial. And its roots are called zeros of the system. And ds is called denominator polynomial. Denominator polynomial. Its roots are called poles of the system. We prove that poles are same as eigenvalues. They will be same. So if poles are same as eigenvalues, obviously stability will depend on eigenvalues. So if poles are eigenvalues, that will decide stability of the system. And eigenvalues of a system do not depend on what kind of excitation is given to the system, what is the external source, and it doesn't depend on what you are taking measurement out of the system. Eigenvalues are a property of the system. So the denominator of a transfer function is always fixed. It doesn't change on sensors or actuators. The numerator changes with sensors and actuators. Denominator does not change with sensors and actuators. It gives you same as poles or eigenvalues of the system, which decides stability of the system. That must be very clear. Okay? Because henceforth, whenever I teach and after me, Professor Kinshuk Bhattacharya teaches all kinds of stability issues, okay, you should identify that those stabilities are basically related to eigenvalues of the system, nothing else. And that stability does not depend on what is the input, what is the measured quantity. Okay? So it's not dependent on input, its exciter doesn't depend on the sensor. So that is all for today. If you have any questions, you can ask me.